We all know that digital computers changed virtually every aspect of our life. Well, the arrival of quantum computers could be even more historic than that.
Some breakthroughs don't just advance technology, they shake the foundations of what we think is real. Google's latest quantum computer, Willow, might be doing just that. Capable of calculations beyond our wildest dreams, it's producing results so strange that even seasoned experts are baffled. Some believe Willow's behavior isn't just advanced computing. It could be evidence of something far more profound. Is this machine tapping into hidden dimensions? Could it be our first glimpse into the multiverse? And if so, what else is out there? Join us as we reveal some of the evidence that Google's quantum computer found of the multiverse. Google's quantum leap into the multiverse. Google's latest quantum marvel, Willow, is shaking the foundations of science with a mind-blowing leap in computing power. It recently pulled off a jaw-dropping feat, solving problems so staggeringly complex that even the fastest classical computers would need more time than the age of the universe to crack them. At the center of this quantum revolution is Hartmut Neven, founder and head of Google's quantum AI lab. Neven believes that Willow's incredible speed may not be due to raw power alone, but something far stranger, something that borders on science fiction. According to him, the machine's uncanny ability may come from performing calculations across parallel universes. That's right, multiple realities working together to help one machine solve problems. This theory is rooted in what physicists call the many worlds interpretation of quantum mechanics. The idea is wild but taken seriously by many in the quantum field. Every time a quantum event happens, the universe splits. One event, countless outcomes, infinite universes. And now, Google may have built a machine that actually uses them. Recent upgrades to Willow include real-time error correction and a clever stacking method of qubits, those tiny, ghost-like units of quantum data. These advancements allow Willow to remain stable, even in a chaotic environment full of interference and noise. Until now, quantum computers have struggled with this fragility. A single stray particle or tiny vibration could ruin a calculation. But Willow seems to have overcome that, finally clearing a path to practical, powerful quantum computing. Neven and his team insist that this is more than just a tech breakthrough. It's a glimpse into how reality might truly work. In a TED Talk months before Willow's latest success, Neven explored how its performance might support the multiverse theory. He even ventured further, suggesting that our very consciousness might be the result of interactions between these endless universes. Imagine that. Your thoughts, your identity, shaped by countless versions of yourself converging into one. If Willow is really tapping into other universes to compute faster, then we're not just advancing technology. We're stepping into a new understanding of existence itself. The line between science and philosophy is blurring, and what was once speculative fiction may be creeping into scientific fact. As the scientific world begins to explore what once seemed impossible, we have to ask, are we on the verge of a discovery that could change our understanding of the universe forever? A new Galileo moment? Imagine the head of Google's quantum artificial intelligence lab seriously discussing things like tiny wormholes you could travel through, crystals that exist outside of normal time, and computers performing precise calculations across parallel universes. It sounds like science fiction, or even madness, but these are precisely the kinds of ideas now being explored at the forefront of quantum research. Even more astounding, some experts believe that quantum computers might someday help expand human consciousness across space, time, and the very complexity of existence itself. As bizarre as that may sound, history reminds us that truly revolutionary ideas often begin this way: rejected, mocked, and seen as absurd. Consider Galileo Galilei. In 1633, he was tried and convicted of heresy for advocating the idea that the Earth orbits the Sun. Despite providing clear evidence and a strong defense, the Catholic Church declared him guilty and placed him under house arrest for the remaining 8 years of his life. The official judgment even forbade him from speaking publicly, essentially banning him from giving the TED Talks of his time about his radical claim that the Earth moves and the Sun stays still. To us today, Galileo's view is basic science, but back then it was a bold contradiction to everything people believed and observed. After all, anyone could look up and see the Sun move across the sky. It took until 1992, over 350 years later, for the Church to formally reverse that judgment. Quantum computing may be in a similar position right now. Like the heliocentric model in Galileo's time, the quantum world challenges everything we think we know. At its core lies a concept known as the many worlds interpretation. This theory suggests that every time a quantum decision is made, the universe splits, creating an infinite number of parallel realities. According to some researchers at Google, quantum computers like Willow may actually be utilizing multiple realities to perform faster, more powerful calculations than anything previously possible. And it doesn't stop there. Hartmut Neven, head of the Quantum AI Lab at Google, has hinted that the full potential of quantum computing could even help us explore the most profound questions about the mind and consciousness. He and his team have speculated that interacting quantum systems across many parallel universes might somehow be tied to how human awareness works. If true, this would mean quantum computers are more than just tools. They could be the first machines to touch the deeper layers of what it means to be alive and aware. Of course, many scientists still view such claims with skepticism. Quantum mechanics is notoriously tricky, and no one fully understands how it all works yet. Yet, brushing off these bold ideas might echo the mistakes of the past, like when the Church dismissed Galileo's discoveries because they defied tradition and common sense. Are we at risk of ignoring something just as groundbreaking, simply because it feels too strange to be true? Cracking reality itself. To truly understand the power and promise of quantum computing, we must first dive into its connection with the very structure of reality. Quantum computers don't just crunch numbers faster. They calculate in a completely different way. Instead of solving problems one by one like traditional machines, they explore many possibilities at once, operating across a mysterious and invisible landscape of probabilities. But what happens when these immense capabilities are applied to something like artificial intelligence? Could AI not only get smarter, but also become something entirely new? These questions may sound far-fetched, but they're not science fiction anymore. As incredible as it sounds, today's progress in quantum computing and AI suggests that humans are creeping closer to that fictional future, perhaps faster than anyone expected. Quantum computing is now accomplishing what once seemed flat-out impossible. The controversy over multiverses, where multiple versions of reality coexist, has been reignited thanks to a bold claim from Google. Their quantum computer, Willow, recently completed a major benchmark test called random circuit sampling in only 5 minutes. Why does that matter? Because the same task would take the world's fastest classical supercomputers about 10 septillion years to complete. That's 10 followed by 24 zeros, a number so large it's nearly incomprehensible. To put that into perspective, our entire universe is about 13.8 billion years old. That means Willow's 5-minute achievement is something that would take a normal computer almost 1 billion trillion times the age of the universe to finish. This isn't just a speed upgrade, it's a whole new dimension of computing power. And it's forcing scientists and philosophers alike to rethink what's truly possible. Some experts believe the many worlds theory of quantum physics could explain this incredible speed. In this interpretation, every possible outcome of a quantum event happens, but in a separate parallel universe. So when a quantum computer like Willow runs a calculation, it might be tapping into countless versions of itself across these universes, all working together to find the answer. It's a staggering idea, a machine solving problems not just faster, but by pulling help from alternate realities. Now, imagine applying this power to artificial intelligence. AI systems trained using quantum computers could gain access to enormous decision trees, explore creative solutions far beyond human imagination, and perhaps even develop forms of awareness we can't yet understand. Could this kind of thinking machine eventually become conscious? Could it experience emotions or create a sense of purpose? The possibilities are both thrilling and terrifying. We might unlock solutions to the world's biggest problems, like disease, climate change, and energy shortages. But as we cross this threshold, new questions emerge. What if machines become conscious? What rights would they have? Would we still be in control? Or would we become passengers in a future we don't fully understand? Also, what strange new forces are we unlocking when we dive into the heart of quantum computing itself? The strange power of qubits. How can a computer complete in 5 minutes what would take a traditional supercomputer longer than the life of the universe? The answer lies in the mysterious heart of quantum computing, qubits. These tiny building blocks are nothing like the ones and zeros we're used to in classical computing. They follow the wild, unpredictable rules of quantum mechanics, where reality is stranger than fiction and possibility stretches far beyond common sense. Unlike classical bits, which can be either a 0 or a 1, a qubit can exist in a superposition, a fuzzy blend of 0 and 1 at the same time. Until it's measured, a qubit is not fixed. It's both, or neither, or somewhere in between. This strange in-between state allows quantum computers to process many outcomes at once, exploring entire fields of possibilities in parallel. It's like reading every page of a book at the same time instead of one by one. But these delicate states don't come easily. Google's qubits require extreme conditions to function. They only work inside supercooled, ultra-clean chambers, refrigerated environments colder than deep space. Within these frosty vaults, the qubits float in a state of near-perfect stillness, shielded from almost everything. Even a stray vibration or a single warm particle could ruin the fragile quantum state. That's why building and maintaining a quantum computer is one of the most challenging tasks in science today. To measure a qubit and cause it to collapse from its shadowy superposition into a definite 0 or 1, researchers use carefully tuned microwave pulses. These signals are aimed with precision, designed to coax a reading from the quantum fog gently. The collapse itself is a mysterious moment, a wave becoming a particle, maybe turning into a certainty. This is the essence of superposition, but it's not the only strange property in the quantum toolbox. There's also entanglement, a phenomenon so bizarre it even troubled Albert Einstein. When two particles become entangled, they're linked no matter how far apart they are. Measure one, and you instantly know the state of the other, even if it's on the other side of the galaxy. Einstein called it spooky action at a distance, and for a long time, many physicists doubted it was real. But repeated experiments have proven it again and again. Entanglement is real. We just don't fully understand why. Quantum entanglement and superposition are not just theoretical oddities. They are essential ingredients in the design of modern quantum machines. These behaviors allow qubits to cooperate in ways that classical bits never could. Together, entangled and superposed qubits form a web of possibility, allowing quantum computers to tackle problems that would take ordinary machines billions of years or longer. The strange power of qubits pulls us deeper into a world where logic bends and boundaries blur. Still, not everyone is satisfied with the way we explain these phenomena. One of the biggest mysteries is the measurement problem. The idea that simply observing a qubit can influence its behavior. How can something as passive as observation decide the fate of reality? It's unsettling, and no one fully agrees on why it happens. Even with our fastest quantum machines, some questions remain maddeningly unanswered. But what if those unanswered questions are pointing to something even bigger? Something that could challenge the very speed limits of the universe. Quantum entanglement, the speed of light, and the possibility of faster-than-light travel. Quantum entanglement is one of the strangest, most fascinating mysteries in physics. It describes a deep connection between particles that seem to know each other's state instantly, no matter how far apart they are. To protect the foundational idea that nothing can travel faster than the speed of light, mainstream science claims that entangled particles don't actually send any signals between them. The randomness of the measurement results, they say, means nothing is truly transmitted. According to the standard view, this preserves Einstein's theory of relativity. But not everyone buys this explanation. A growing number of scientists and theorists argue that the speed of light might not be an absolute limit after all. These anti-establishment thinkers propose that entanglement could hint at deeper, faster connections woven into the fabric of reality, connections that might allow for faster-than-light travel or communication in some form. If they're right, the barriers keeping us isolated from other star systems might one day crumble. This radical idea gains more credibility when viewed through the lens of the many worlds interpretation of quantum mechanics. First proposed in 1957 by Hugh Everett in his paper The Theory of the Universal Wave Function, the many worlds interpretation, or MWI, suggests that every quantum event splits the universe, creating a near-infinite number of parallel realities. Instead of randomness, there is branching. Every possible outcome happens, just not all in this universe. The many worlds idea has attracted respected supporters, including physicists Bryce DeWitt, David Deutsch, Max Tegmark, and Sean Carroll. Deutsch has even speculated in the beginning of infinity that alternate histories, such as fictional worlds or imagined timelines, might actually unfold in real universes, so long as they obey the laws of physics. Max Tegmark and Sean Carroll have publicly explored these theories as part of serious scientific discussion, not science fiction. Could this explain how qubits in a quantum computer work so mysteriously well? Quantum computers, including Google's groundbreaking Willow chip, rely on entanglement to function. By linking qubits, quantum bits, in a shared, interconnected system, these machines can perform computations far beyond what classical computers can even attempt. Qubits use superposition, being in multiple states at once, entanglement, instant links between particles, and quantum interference, where certain outcomes cancel each other out to process huge amounts of data simultaneously. This kind of raw quantum power comes to life in one key challenge: the random circuit sampling benchmark, a task so complex that even the fastest classical computers fail to crack it in any reasonable time. But what does it feel like when a computer steps into the realm of the unthinkable? Cracking the quantum maze. To truly understand the power of quantum computing, imagine being dropped into an impossibly complex maze. Your job is to explore every path, note every turn, and record where each one leads. In quantum computing, that is the goal of the random circuit sampling test. In this metaphor, the maze is a random quantum circuit. a mind-bending structure made up of gates. These gates aren't physical doors, but mathematical instructions that guide how quantum bits, or qubits, behave and interact. The layout of these gates in the RCS test is random, which makes the entire circuit behave unpredictably. The goal is to sample the outputs of this maze-like quantum system repeatedly to uncover patterns in its behavior. The result is a map of probabilities, a fingerprint unique to the specific circuit. For classical computers to simulate this process, they'd need to calculate every possible path through the circuit one by one. But here's the catch. As the circuit gets bigger, the number of possible paths grows exponentially. Even the fastest supercomputers in existence would need septillions of years to complete the task. This is why the RCS test is such a powerful benchmark. It's not meant to solve a real-world problem directly. Rather, it's designed to highlight the one thing quantum computers can do better than anything else: handle extreme complexity at near incomprehensible speeds. It's a way to prove quantum supremacy, the point where quantum machines outperform classical ones in a meaningful way. Until recently, that supremacy was theoretical. Quantum computers were plagued by noise, tiny random disturbances like stray particles or microscopic vibrations that disrupted their delicate systems. This noise made it nearly impossible to perform large-scale quantum calculations without errors. But in December 2024, Google announced a stunning breakthrough. Their quantum chip, Willow, successfully completed the RCS test without being derailed by noise. They achieved this by scaling up the number of qubits and implementing real-time error correction, a feat long thought to be years away. Willow's success means that quantum computers can now explore all those tangled paths in the maze at the same time. Thanks to quantum phenomena like superposition and entanglement, these machines can sample outputs in a way that traditional computers simply can't. Instead of trudging through the maze step by step, they seem to know all the paths at once. This unlocks a future filled with staggering possibilities. Quantum computing could revolutionize everything from medicine to materials science, climate modeling to cybersecurity. It could supercharge AI, allowing machines to generate answers and ideas at levels we haven't yet imagined. It might even help simulate complex realities, like weather systems, molecular structures, or entire worlds. Some thinkers, like Elon Musk, believe this technology could eventually confirm the idea that we're already living in a simulation, crafted by an ultra-advanced civilization. It's a wild notion, but as quantum computing continues to advance, what once sounded like science fiction starts to feel uncomfortably plausible. If quantum computers solve the impossible, what will that mean for our reality? Are we ready for the answers they might reveal?